So, hello, welcome to today's problem solving session. This is the week 5 problem solving sessions that we'll be dealing with. I think we'll wait for a couple of minutes to see if any more people are entering, and then we'll get into the classes. Okay, so we'll start with the class. So this week we'll be dealing with the questions that we'll be using to submit the next assignment. And the topics that we'll be covering today will be based on the week 6 lectures, that is focusing more on coagulation and flocculation and filtration. So these are the contents of the week 6 lecture. The theory behind coagulation and flocculation, the design of the clariflocculators and rapid mixtures that is associated with the process. Then there is what is the theory behind filtration, about slow sand filters and rapid sand filters, as well as pressure filter, and some problems that are based on it. So we'll go into the questions discussion. So the first question is, which of the following adequately describes the properties of colloidal solid particles? You have 4 options here, and I'll give you a minute or a few seconds to answer the questions, and then we'll move on to the solution. Okay, so let's move on to the solution. So if you look at the particles that will be available in water, we have classifications based on the size of the particles. So if you see, there will be dissolved particles, then comes colloidal particles, and then comes suspended or settlable solids. So all of these vary in their size, like you can see on the slide. Dissolved solids are less than 1 nanometer in size. Colloidal solids or non-settlable solids come between 1 to 1000 nanometers in size. and suspended or settleable solids will come in sizes greater than 1000 nanometers in size. So like the question that is asked here is about what is describing the properties of colloidal solid particles. Another name for the colloidal solid particles is non-settleable solids. So with respect to their properties, you can say that colloidal solids, in comparison to dissolved and suspended, they are electrically charged, but they're not as small as the dissolved solids. Although they're charged, they're not as small, and they can be seen under a high-powered microscope. But they're not big enough. They're not big enough to be filtered also. So other methods have to be adopted to remove these particles from the water. So dissolved solids, although they are electrically charged, they are small. It is not visible to the eye. It cannot even be seen under microscope also. Colloidal solids vary in that they also have charge and everything, but the only thing they are a little bit bigger in size than dissolved solids, and they can be seen under a microscope. Whereas suspended solids, they are large enough for our eyes, and they can also be seen with the eyes, and they can be removed by filtration, and they also have a tendency to settle. The colloidal particles, since they are electrically charged, they are difficult to settle down. So the answer for this question is option 3, electrically charged and which cannot be removed through simple filtration. The first one is first one would be the answer for dissolved solids. Second one would be the answer for suspended or settleable solids. So moving on to the second question. The most common approach of removing colloidal particles from water is? Hi Sangamitra, if you know the answer, you can um, share it in the chat box. Okay, so moving on to the answer to this question. The most common approach of removing colloidal particles from water is combined coagulation and flocculation. Now, like in the first question, we had discussed about the size of the particle, basically the diameter of the particle, and the classification based on this. So we had also read about the size of colloidal particles between 1 nanometer and 1000 nanometer, which is nothing but 1 micron. So if you see here, the settling time for colloidal particles are ranging from 8 days to 200 years and all. So it is not easy to make them settle by the process of sedimentation. It is not enough to keep it for settling, and that these particles are not going to settle majorly because of the electrical charge, and how it is going to keep the particles in motion because of the charge. So for that, for such particles, it is necessary that we adopt processes like coagulation and flocculation. So the answer for this question is going to be coagulation and flocculation. The third question, identify the correct sequence of a typical coagulation and flocculation mechanism. So coagulation and flocculation. occurs in various steps. I mean, there's an entire mechanism of this process that happens. So, what is the sequence of this process? There are various names for each processes that is happening for this coagulation and flocculation to happen. So what is the sequence of this? Okay, I'll move on to the answer. So, if you see here, the coagulation and flocculation happens in this sequence. First, the charge neutralization will occur. Then, sweep coagulation will occur. After that, bridging occurs, and then the patch flocculation will occur. So, charge neutralization is nothing but these colloidal particles are electrically charged, like I said earlier. So, what happens is when two colloidal particles are close to each other, they start repulsing each other. So the first process that has to happen is to bring the colloidal particles together. And in order to bring the colloidal particles together, it is necessary that we neutralize the charges of these particles so that they will come together. So when, after the particles charge has been neutralized, there will be coagulants added, which will help in bringing these colloidal particles together, which is called bridging. And patch flocculation is when after they come together, they form flocks. That is a process called patch flocculation. Sweet coagulation is nothing but when we add coagulants, the coagulants itself forms precipitation. So this precipitation, what it will do is this precipitation, even if the colloidal particles charge is not neutralized, this precipitation will sweep all the coagulants and catch all those coagulants in the water as it moves through the water. This process is called sweep coagulation. So when a coagulant is added, it will first uh, create attractive forces between the colloidal particles by neutralizing their making the charges opposite. Then it will itself form precipitates that will sweep up all the colloids in the water, even if the charge is not neutralized. If the charge neutralization is not occurred in the colloid particles also, they will catch all these colloids that is present in the water and trap it, and while it moves down the water. Then after that, after the charge neutralization, these colloidal particles have a tendency to come together to each other. That is called bridging. And after bridging happens, flocks will occur or flocks will form. That is the process of patch flocculation. So the correct sequence is charge neutralization, sweep coagulation, bridging, and patch flocculation. Okay, so moving on to the next question. Question number 4. Match the appropriate coagulation practices concerning the colloid volume and alkalinity levels in water. Hi Sangam Mitra, if you know the answer, you can put it in the chat. Hello. Okay, I'll move on to the answer. So basically what we are talking about when we say high colloids is the concentration of colloids. If the colloids are in high concentration, and concentration is also measured in terms of the surface area, because when colloids are more, in the volume is more, the surface area, that is the number of colloids are going to be more, so surface area is also going to be more. So it is measured, or it is uh, represented in terms of surface area. So when there is high concentration of colloid and the water is low alkali, and the alkalinity of water is low, we don't have to be concerned about anything, because coagulation happens best when the pH of the water is lower. So we don't have to worry about the amount of coagulant that we are adding, or whether there will be an overdosing process or anything. So that is what happens when the colloid concentration, or when it is high colloid, low alkalinity condition. Now, when the when the colloid concentration is high and when the alkalinity is high, what we have to do is we have to make the water less alkaline. We have to bring the condition to low alkalinity, either by neutralizing the pH or by adding acid to the water to lower the pH. Whichever is an economical method, we will adopt that, and we will bring the alkalinity to a low alkalinity level. Now, suppose if the condition is very low concentration of colloid and high alkalinity, we can either destabilize by the dosage to give sweep flocking by by the sweep coagulation, sorry, sweep flocculation process. This colloids can be removed, or they can coagulant aids can be added. Coagulant aids are nothing but that is materials like bentonite, which will actually help in reducing the dosage. It will help in so that we only need to add less amount of colloid. So coagulant aids are such materials. Bentonite is one such material. So if you add bentonite, we don't have to add high dosages of the coagulant. So by this method, we can is adopted when the colloid concentration is low and when the alkalinity of water is high. So in case the colloid concentration is low and the alkalinity is also low, this is a very difficult case. So we have to add the alkalinity of colloids, and also sweep flocculation is also difficult to take place in such a water. So this is not a very ideal condition for coagulation to occur. So when you match this, we can see high colloid, low alkalinity. We can add direct coagulant addition with less concern of overdosing and pH maintenance. High colloid, high alkalinity, we can add high coagulant dose at high pH, or add acid to lower the pH and then add coagulant. So it is A2, B3, C is 1, D is 4. So this is the answer for the fourth question. Now moving on to the fifth question. Compute the power transmitted by a circular rapid mixture with a detention time of 20 seconds, a relative velocity gradient of 900 per second, if the design flow is 1200 meter cube per hour, by assuming the dynamic viscosity as 8.9 into 10 to the power minus 4 Newton second per meter square. So this requires using these formulas. We know the tank volume as Q into T, discharge into detention time. Then power is calculated by mu v g square, where mu is the dynamic viscosity, v is the volume, g square is the velocity gradient given in per second. So it is using these two formulas that this problem will be done. So if you can do it, it would be nice. It would be good if you could do it and give the answer here. Okay, so I'll move on to the solution. So coagulation occurs in tanks called rapid mixtures and flash mixtures. They are nothing but tanks which is aiding in the process of coagulation by using a fan-like structure or mixer-like structure that is going to circulate the water and help in these after the coagulants are added, help in these colloidal particles to come together. So that is what is called a rapid mixture or a flash mixture, flash mixing tank. Flocculation is done in flocculation basins, either baffled channel flocculators or paddled flocculators. Baffled, like in the last class we had explained, they are partitions like this. You can see these black partitions over here. They are called baffled. Paddles are nothing but again, paddle-like structures that will help in mixing water. And if for combined flocculation and sedimentation, tanks called clariflocculators are used. Now, with regard to this question, in case of designing of rapid mixing unit, we need to know the design flow that is going to be coming into the tank, which is Q, and the detention time in seconds. Generally, detention time in time of these rapid mixtures are considered to be in the range of 20 to 60 seconds. That is, the particle has to stay in there for 20 to 60 seconds for the coagulation process to happen. So we can calculate the volume of the tank using the by multiplying the discharge rate with the detention time. Power requirement is calculated using this formula here, which is mu v g square, where g is the velocity gradient obtained by dividing the relative velocity by the distance between them, the distance between the two particles. So that will give us a velocity gradient. Here in our question, velocity gradient is given. The volume of the tank is not given. The discharge rate is given. Detention time is given. Velocity gradient is given, and dynamic viscosity is given. So this can be calculated using the discharge value, which is 1200 meter cube per hour, which is given. We have to convert it into meters per second because all the other values are in terms of meter and seconds. So that will give us this value. We also have time is equal to 20 seconds and the dynamic viscosity. So required volume is equal to the discharge rate was multiplied by the detention time, which is giving us 6.66 meter cube as the tank volume. Now using the formula P is equal to mu v g square and substituting the values directly in this 8.9 into 10 to the power minus 4, the dynamic viscosity, volume of tank in meter cube, and velocity square of the velocity gradient, we will get the answer in terms of kilowatt, which is 4.8 kilowatts. So the answer is equal to D. So the answer here, when the values are substituted, we will be getting it in Newton meter per second in watts, and we have to the answer here provided is in terms of kilowatt. So that is how we are going to get 4.8 kilowatt. Okay. So that was a numerical with regard to coagulation. Moving on to next question. Again, in this question number 5, what is the approximate depth of the rapid mixture? So this is also something that is coming under the design category. So under the design conditions for a rapid mixer, there is a formula or there is a condition of the depth. So if you know that, you will be able to find out this answer. Which I can say, okay, it is 1.5 times the width of the tank, otherwise diameter of the tank. If the tank is rectangular, it is 1.5 times the width. If it is circular, it is 1.5 times the diameter. So using that value, we can find out the depth of the tank. Okay, moving on to the answer. So, like I said, the depth is usually taken as 1.5 times the diameter of circular tank, so 1.5 times the width of the rectangular tanks. So, in case of this question, here they have given that the tank is circular. So, we'll be taking the diameter of the tank. So, it is 1.5 times the diameter. Now, we know the tank volume. We had calculated the tank volume to be 6.66 meter cube. So, 6.66 meter cube is obtained by multiplying the depth of the tank with the surface area of the tank, or the cross-sectional area of the tank, which is nothing but pi d square by 4, and the depth is equal to 1.5 times the d. Since we have the volume, we can find out the diameter from this value. The diameter is equal to 1.056 meter. So the depth will hence the depth will be equal to 1.5 times the diameter value, which is 1.6 meter. So the answer is going to be 1.6 meter. So you have to be in this question. What is the catch is we'll find out the diameter of the tank, and then don't go on to the answer and don't go on to the solution and take up the answer which is 1 meter or anything. We have to go one step ahead and also calculate the depth of the tank, which is the question. So that is one catch that is coming in this question that can be a little misleading. The next question, a high velocity gradient and channel flocculator can be generated by. Okay, moving on to the answer. So, like I said, flocculators, there are two types. One is the baffled flocculators, the other is paddle flocculators. Baffled flocculators are making use of these partitions called baffles, which is actually helping in plug flow. This also we had studied in the last session, where water in batches through these baffles will flow and reach into the flocculation tank. So the flocculators can be either horizontal flow, as you can see here, water will enter and it will go on like this. This is the top view of the horizontal flow, and this is a vertical flow flocculator. So here the question is, what is going to give us high velocity gradients? So if the spacing of the baffles are close, that is, if these baffles are closely spaced together, we will get higher velocity gradient, and if the spacing is wider, we'll get low velocity gradient. So that is how we can change the velocity gradients of the water that is entering, or the water that is entering the flocculators, by changing the spacing of the baffles. So here the answer would be A, that is by closely spacing the baffles, we can obtain a high velocity gradient. If you keep the spacing of baffles wider, you will get a lower velocity gradient. Short circuiting is nothing but when the particles in the water, without staying in the tank as per the detention time requirements of the tank, without staying in the tank, it goes out of the tank without getting settled, then you call that a process, you call that short circuiting. This is a condition which is going to make the coagulation or flocculation tank inefficient. So yes, that is for this question. Now moving on to the next question. Determine the coagulant dose ensured by adding 4 milliliters of ferric chloride in a 2-liter jar. Okay, so I will move on to the answer. So this is one practice problem from the lecture with regard to the concentration of the coagulant dose that has to be added. So here they are saying that we are supposed to be computing the coagulant dose. When we add 4 ml of FeCl3. So coagulant stock given over here is 2000 milligram per liter. That means that 2000 milligrams milligrams per 1000 ml. Since it is in ml over here, we are trying to convert it in terms of ml. So 2000 coagulant stock is 2000 milligrams of it in 1000 ml. 1000 ml of this of the coagulant. So for 4 ml of coagulant stock, how much of milligrams of coagulant would be there? That you can do by multiplying 2000 into 2000 into 4 divided by 1000 will give you what is the amount of coagulant that will be there in 4 ml of coagulant stock, which is 8 milligrams of FeCl3. So we have 8 milligrams of FeCl3 in a 2-liter jar. That is what is given here. 4 ml of FeCl3 in a 2-liter jar. So we have 8 milligrams of FeCl3 in 2-liter charge, a 2-liter jar. That is equal to 8 divided by 2, 4 milligram per liter in the of coagulant dose in the jar. So this is also one numerical that is important. So again, here they have given the coagulant stock as 2000 milligram per liter. We are converted in terms of milliliters. Then we are calculating for 4 milliliter of coagulant stock, how much of grams of FeCl3 is there. We got that value. That divided by the by 2 liters is giving us the milligram per liter dosage of FeCl3 in the jar. So moving on to the next question. Which of the following statements are correct regarding a clariflocculator? Like I said, clariflocculator is one where flocculation and sedimentation both occur simultaneously. It's a tank where both of it will occur. So what are the statements that are right or right with regard to a clariflocculator? Again, these are design conditions which you should be familiar with. So is in a clariflocculator, the inner tank serves as a flocculation basin and the outer tank serves as a clarifier. Type 2 settling of flocks is happening. Then detention time is usually between 10 to 40 minutes for the flocculation zone, whereas in case of the clarifier zone, it is 1.5 to 4 hours. Which out of the following statements are correct? Is it 2 and 3, 1 and 3, or statement 2, or whether all the statements are true? Okay, so I'll move on to the answer. So in case of a clariflocculator, that is, it comprises of a flocculator as well as a clarifier. Clarifier is for the sedimentation part, flocculator is for the flocculation part. So clariflocculator is a combination of flocculation and clarification. The inner tank, as you can see here, this is where the flocculation happens, and this is the flocculation tank. And the outer ring over here, or the outer tank, is the clarifier. So the first point over here is saying the inner tank serves as a flocculation basin and the outer tank serves as a clarifier. So that statement is true. Now, the second one is what kind of settling is occurring in the clariflocculator type 2 settling, that is flocculant settling is happening. So that statement is also true. The third statement is about the detention time of the flocculation zone and the clarifier. So here you can see the detention time. Detention time over here is given in the design criteria. We have the inlet zone, the flocculator, inlet zone which is a flocculator, then the outer zone is the clarifier, then there's a sludge zone where the sludge is collected and removed, and the clarified water will move out of the clarifier. So in case of clariflocculator, the detention time for the flocculator over here, if you look carefully, is 10 to 40 minutes. And the detention time for the clarifier over here is 1.5 to 4 hours. So our statement 3 is also correct. So the correct answer for this question would be D option, all statements are true. That is a clariflocculator, inner tank is flocculation tank, outer tank is a clarifier, type 2 settling, that is flocculation type settling is occurring, and the detention time of the flocculation basin is 10 to 40 minutes, and the clarifier is 1.5 to 4 hours. So we have to be familiar with the design conditions of all these tanks that is used for coagulation, flocculation, clariflocculators, etc. Now, what is the major filtration mechanism happening in a multimedia filter? Now, we are moving on to the filtration part of this water treatment process. This question is about the filtration. What is a major filtration mechanism occurring in a multimedia filter? Okay, so moving on to the answer. In filtration, some of the processes that is occurring is a physical straining. That is nothing but particles. Filtration is the process where materials like sand, gravel is used for capturing the flocks and the other impurities in water that is coming out of the flocculator. So if the particles are larger than the pore size between these filter media, physical straining is occurring. Another process that is occurring is sedimentation, that is particles will settle on this filter media. The third process occurring is adsorption, that is the filter media, materials in the filter media is going to absorb the particles. They're going to attract the particles towards the surface and it is going to stick onto it. So this is the major mechanism occurring in multimedia filters. Also, apart from that, biological actions, that is in between the filter media there will be organisms which is going to catch the particles and decompose it. In this form it is going to remove the it is going to remove the particles from water. Absorption is also happening, electrolytic action is also happening. So in this question they have asked about the multimedia filter. What is the major filtration mechanism occurring in a multimedia filter? The major mechanism that is occurring in a multimedia filter is adsorption. So the correct answer for this question is option C. Now, question number 11. Pressure filters are more feasible for application in. Where are pressure filters majorly used? Okay, I move on to the answer. So, like using when we use, there are two types of filters that is used during filtration: slow sand filters and rapid sand filters. Both the filtration techniques, um, filter material is used, but there's no pressure that is applied on water. Water is led to there's a certain amount of depth the water has to be poured into the tank, and that depth is what is actually uh, required. But in case of pressure filters, a pressure is applied. So pressure filters are majorly used. If you go through the slide, you will know what a pressure filter is and what is the requirements of a pressure filter. But typically, pressure filters are used for high quality surface water that is not requiring clarification. Also, this is used for removal of iron and manganese in addition to the turbidity of groundwater. Also, these are majorly used in small plants, industrial industries, and swimming pools. One major use of pressure filters is in the swimming pools. So, if you see here, all of the above will be the answer because yeah, it is used in small factories, so plants, swimming pools, and industries as well. So the answer for question number 11 would be all of the above. Moving on to the 12th question. A typical method of cleaning the slow sand filter bed is, like I said, there are two types of filtration that you're, two to three types of filtration that you're learning. Rapid sand, using rapid sand filters, slow sand filters, and pressure filters. So all three of it has got different design considerations. In case of slow sand filters, what is the method of cleaning that is adopted is the question over here. Is it backwashing with water under pressure? Is it by using compressed air agitation of the sand bed, or is it by scraping the top sand and replacing it with new sand, or all of these methods are used? Okay, I'll move on to the answer. So slow sand filters, there is a particular type of maintenance that is to be fulfilled in case of slow sand filters. And in this maintenance method, the cleaning process is done by scrapping. That is, a top few centimeters of sand is carefully scraped off using mechanical scrapers, and a new layer of the clean sand is exposed. So if you have this a thickness of the sand material, which is one of the filter material, after a while, the because of the accumulation of impurities on it, it is going to be inefficient. So in order to maintain the efficiency of slow sand filters, the top layer of the slow sand, the filter material of sand is removed, so that the bottom material, which is relatively cleaner, is exposed. And this process is continued until a particular thickness of the soil, the sand material, sand filter media is reached. After that, they have to uh, renew it with a new thickness of sand layer. So the answer here is, again, if you see this slide also, they are going to be cleaning by scrapping 2 to 3 centimeters of sand from the surface and replacing it with new sand or exposing it to the new sand. It is in rapid gravity filters, that is backwashing. Cleaning is done using backwashing. That is from underneath the water is water is brought to the top, so that all the impurities will get removed from the filter media. So the answer is option C, scraping the top sand and replacing it with new sand. Backwashing with water under pressure is a maintenance technique that is used in rapid sand filters. Compressed air agitation is also used in rapid sand filters. You can refer the slide for uh, the comparison between slow sand filters in terms of the filter media, the requirement of water, the kind of operation that happens, and maintenance technique that is being used in these types of filters. Moving on to the next question. As per the guidelines provided by these bodies, a maximum of 4 slow sand filter beds for an area between 250 to 649 meters square are recommended, based on which a slow sand filter with 5 beds were designed. What is the approximate minimum volume of water that can be treated in these filter beds while maintaining a flow rate of 0.175 meter per hour? So maybe you can go through the question once more, and then we move on to the answer. So as per certain design criteria, we have a recommendation of 4 slow sand filter beds for an area of 250 to 649 meters square. So within this area, we can provide 4 slow sand filter beds. And 5 beds were designed based on this. What is the volume of water that can be treated in this filter beds is the question. They have given us the flow rate. So 5 filter beds are provided. In these 5 filter beds, what amount of volume of water can be treated or water can be filtered for this flow rate is the question. Okay, so I move on to the solution. So if you look at the lectures, we have design conditions for slow sand filters and rapid sand filters. And in case of a slow sand filter, the recommendations are 4 beds for an area of 250 to 649 meters square. Now, we have the flow rate and the minimum area or of each bed is going to be 650 meters square. And we know that we have 5 beds. So total area would be 5 into 650. So since they have said that the area for areas between 250 to 650 for maximum efficiency, we are going to be using this value. So say if this is the value of the area of the bed, we have 5 beds. So when we multiply these two values, we get the total area. Now we have the total area and we have the flow rate also. So flow rate is equal to 0.175. We know that Q is equal to A into V. So substituting 0.175 is equal to 325 by dividing the flow rate. This thing is wrong over here. You have to be dividing these values, not multiplying it. It is area into area into what is the minimum volume of water that can be treated in this filter beds. So we have the flow rate, area in divided by the detention time is going to give area into the velocity is going to give us the flow rate. So since we have the velocity over here, flow rate is given in terms of meters per hour. So this is correct. Okay, so we can multiply the area into the velocity. It will give us the flow rate, that is 13,650 meter cube per day. So it is actually velocity is given and they want us to find the flow rate of the water that is supposed to be flowing into this filtration tank. So it is 13.65 million liters per day. There's a change in the question. I'll be changing this. I'll be going through the question once again and making some correction if it is required. So here we are doing just using the basic formula of discharge, that is flow rate is equal to area into velocity. Here they have given us a flow rate in terms of velocity. So we'll multiply the velocity with the area which we have from the CPHEO guidelines and the number of beds that is given. Multiplying those two values will give us one value. That value is 13.65 million liters per day. So the option D will be the correct answer. Now moving on to question number 14. What is the average filtration rate in a sand filter with an area of 40 meters square that filters an average of 8,000 meter cube of water in 45 hours. So again, based on the units itself, we can do this question. We can find the solution for this question. They're asking for the average filtration rate. We have been given an area of the filter. 8,000 meter cubes of water in 45 hours need to be filtered. So what will be the filtration rate is the question. So I'll move on to the answer. This is a simple calculation. 8,000 divided by 40 divided by 45 will give us the filtration rate in meter per hour. It is 4.44 meters per hour, which is option A. So the correct answer is 4.45 meters per hour, option A. Average filtration rate, we have been given the area, we have been given the volume of water that needs to be filtered, and the time that is required for this water to be filtered. So if you divide the volume divided by the area into time, we will get the average filtration rate. A simple mathematical question this is. Since we, by knowing the units itself, we can do this question. Moving on to question number 15. So for question number 14, what is the average net daily outflow from the filter if it is backwashed for 24 minutes at a rate of 0.5 meters per minute? So here, question number 14, we have 4.45 meter per hour as the filtration rate or the velocity of water. So they have asked us to find out the daily outflow from the filter if it is backwashed for 24 minutes at a rate of 0.5 meters per minute. So from the total water, 0.5 meters per minute of water, filtration rate of water has been used for 24 minutes. So removing that quantity of water, what is going to be the net outflow from the filter is the question. This is question number 14. We have the average filtration rate here. Here they are asking us for the net outflow after some of the water has been used for backwash. So now, if you see here, the quantity of backwash water computed, we have been given it is 0.5 meters of the rate of water is 0.5 meters per minute. We have also been given for how long this backwashing is done. It is done for 24 minutes. When you multiply these two values, you will get that 0.5 to 24 is giving us the how much depth of water is being backwashed into the area is given in the previous question. Previous question, 40 meter square is the filter area. So multiplying by the area of the filter, we'll get the volume of water that is being used for backwashing. That is 480 meter cube. Now net production of water is going to be 45 hours. That is also given in the previous question. 45 hours of filtration is done plus 0.4 hours, 0.5 hours. So that is for the backwashing. So 8,000 meter cube of water is the amount of water that is being filtered minus the amount of water that is being used in the backwashing will give us 7520 meter cubes of water. That is the net volume of water that is coming out. Now in order to get the rate, the average net daily outflow will divide it by 2 days. That is again an this one design consideration. So dividing it by 2, we'll get 3760 meter cube per day. So we here have 45 hours given and we are keeping an for the backwashing 0.5 hours also. So totally we are having 45.5 hours, say approximately 2 days, which is 48 hours. So that dividing the volume by the day will give us the rate per day, which is 3760 meter cube per day. So this is how this problem is done. Another problem that is has got high probability of being asked during the exams in the chapter filtration. Another question. A water treatment plant is designed to treat 1 meter cube per second of raw water. It has 14 filters, surface area of each filter being 50 meter square. What is again the inflow rate? That is how much of water is coming into the tank is what they're asking in terms of meter cube per meter square per day, with 2 filters out of service for routine backwash. So what they're asking here, they've given us the inflow rate of 1 meter cube per second. The number of sand filters is provided. Area of each sand filter is provided. We have been asked at what loading rate should be water added if 2 filters are not working. Okay, let's move on to the solution. So the capacity of the water treatment plant is 1 meter cube per second is given. Number of filters is given. Surface area of each filter is given. How many filters are out of service is also given. So number of filters in service is going to be 12 because these two are not working. Now loading rate is computed by dividing the quantity of water that is to be treated per day divided by the surface area. That is in the question it has been given what is the loading rate in meter cube per meter square day. So if you divide the volume of water that is that requires to be treated per day by the area of filters, then we will get the surface loading rate. So we have area for one filter which is 50 meters square. Total number of filters is equal to 12. So the total area is equal to 12 into 50. Now we have been given the capacity of the water treatment plant is 1 meter cube per second. Since it is in days that we require, we convert this value into 1 meter cube per day. So for that, we multiply it by 16 to 16 to 24 divided by number of filters into the area. We will get the loading rate 144 meter cube per meter square day. So this the answer for this question is 144. I'll explain once more. We have been given the capacity of the tank. We have been given the total number of filters, out of which 2 are not working. So the filters that are working is 14 minus 2, 12. Each filter area is given. So the total area is going to be 12 into 50. Now loading rate is to be given in terms of meter cube per meter square day. So when we divide this value by the area of the tank, we will get the loading rate. This value, since it is in meter cube per second, we'll divide it, we'll multiply it with, we'll convert it into meter cube per day. After the conversion, we are going to divide by 12 into 50, which is the total area of the filter media, and that gives us the surface overload, loading rate, surface overloading rate, which is 144. Now here again, there are 2 questions based on some data provided. You need to find the answers for that. The city is going to install rapid sand filters using the following data. Loading rate is 200 meter cube per meter square per day. Flow rate is 0.5 meter cube per second. Surface area for each filter box is 50 meter square. So they're asking the surface area required for the rapid sand filter will be. Here, filter box, that is surface area of each filter box is equal to 50 meters square. They're asking the surface area of the rapid sand filter, the whole tank will be how much? And how much will be the number of filters required? Again, if you see the units of this question, you can pretty much do this, solve this question. If you want, you can try and give me the answers. I'll wait for 1 minute.
Hi Shruti, I'm not solving actually. I'm on the way. So I
Okay,
just
okay,
see.
okay. I'll move on with the
Yes.
answer.
Yes.
Okay, so if you see here, we have
As I'm
been.
traveling actually. I'm traveling, so I can't.
It's okay, Sangamitra. I'll move on with the solution. Okay, so the design loading rate given here is 200 meter cube per meter square day, and the flow rate is also given. Since it is given in meter cube per second, when we convert it to meter cube per day, we will get a particular value. Surface area per filter box is 50 meters square. They have asked for the surface area required for rapid sand filters. So when we divide this 0.5 into the design flow rate divided by the design loading rate, we will get a value in area, that is the design surface area required for the rapid sand filters. So like I said, we have the units over here. So if we are the area is required in meter square, it is just a matter of dividing these two values. We will get the answer in area. Okay, now the second question is, how much is the number of filters required? Now we have 50 filters required. So 216 is the total area required. 216 divided by 50 is going to give us 4.32, which is almost equal to 5. So the requirement is 5 filters. Since the option here is not having a value of 5, we will go to the next bigger number, not the next smaller number, next bigger number, which is 6. So the number of filters required shall be 6. So the option C would be the correct answer. Again, since we have the total area required for the rapid sand filter, we have the area of one filter. So total area divided by the area of one filter is going to give us the number of filters that is required, which will be 5 in this case. But again, since in the option we don't have 5, we are going to opt for the option with the value 6, which is option C.
That means we will consider in higher side. We'll
Yes, yes,
consider in higher side as because
yes.
I'm asking 4.32. It is nearer to 4, but it is
No, no,
not
no,
nearer
no,
to 5.
no, no, no,
So we
no.
have to take a higher side. Higher
Yeah,
side.
since it's not just 4, it is 4.32 that is required.
Yes,
So
yes,
we need more than 4 value.
yes,
Again,
yes.
since there's no 5 in this option, we say it is, it's a design question, so we can make modification accordingly. Okay, this question is a theoretical question again. Flocculation is the process that removes algae from stabilization on pond effluent, or is it the process that promotes the aggregation of small particles into larger particles? Or is it the process that helps in removing set level solids? Or is it a process that is similar to filtration? Is a question. Okay, so the answer for this is, so option B. It is a flocculation is a process that is helping in the aggregation of smaller particles. Colloid particles, they'll come together when the charge is neutralized and form larger particles called flocks, which because of the high size will tend to settle down. So this is what is flocculation process basically. Now next question. Particles of size around 1 micron are best removed by filtration, plain sedimentation, chemical precipitation, or chemical coagulation. So we in an earlier slide had talked about the size of the particles and what are the names of classification based on it: dissolved, colloids, and settlable or suspended solids. We had learned that dissolved solids is particles which is less than 1 nanometer. Colloidal particles are in between 1 and 1000 nanometers. 1000 nanometers is equal to 1 micron. And we have also studied colloids are removed through coagulation. So the answer in this question would be option D, which is chemical coagulation. So dissolved solids cannot be removed through coagulation, but colloids can be removed through coagulation and suspended particles through sedimentation. After which you can filter. Coagulation will be done, and after that only filtration will be done. Next question: what is a clarifier? Is it a plain sedimentation tank? Is it an aeration unit, or is it a coagulation sedimentation unit, or is it none of the above? Again, this also we had seen questions related to it. A clarifier is one in which flocculation as well as sedimentation will occur, with the inner tank being the flocculator, outer tank being the clarifier. So the answer for this question would be coagulation sedimentation unit, which is option C. So that's it for today. If you have any doubt regarding any questions, I'll be here. Otherwise, you can exit the meet.
Sir, will you show the answer of question number 10 and 11? I could not able to see actually.
Yeah. Okay, 10th question is talking about the filtration mechanism in the multimedia filter. So multimedia means there are various filtration material, like sand is there, gravel is there, stones that are greater than a gravel size is there. So what is the major mechanism happening in multimedia filter? So adsorption is the process that is majorly occurring in a multimedia filter. Adsorption is nothing but when the solid particles are going to attract, or the impurities are going to stick on to the surfaces of the solid particles. So this was the 10th question. And 11th question is about pressure filters. Where is pressure filters being used majorly? In this case, pressure filters are majorly used in small factories or plants, industries, in swimming pools. Again, since it's a costly thing, it has to have an application which is relating to the cost of this pressure filter. So these are the areas where pressure filters are used. Am I clear, Sangamitra?
Yes, yes, I'm clear. I'm clear.
Okay. Is there anything else? Any doubt? I'll be here.
No, I can leave. I think I'm alone. I think no one else is there now.
Okay. Thank you,
And
Sangamitra. Yeah.
yes, all the details. When shall I get all the details in the site, NPTL site? These questions and details.
Everything is immediately after the class. In 1 or 2 days I'll be uploading the slides and the YouTube video.
Okay. Okay. Thank you. Because I missed few questions. That is why I was asking.
Yeah. Everything will be there in the site.
Okay, okay. Thank you. Okay, I'm
Oh,
leaving.
okay.
Bye.
Thank you, Sangamitra. Bye bye. Good night.
Bye.
Okay, so thank you for attending the session, and we'll meet in the next week discussing about the lecture materials relating to week 7 and solve some questions and go through some theoretical questions that will help you in solving week 7's assignment questions. So have a good night, everybody, and meet you next week. Thank you and bye bye.